Welcome to this explainer. Today, we're diving deep into the absolute fundamental architecture of the internet. We're going to decode the exact addressing system that makes all our global communication possible. I mean, we use the internet every single day, right? Streaming, emails, endless video calls. But we rarely stop to think about the invisible, highly structured digital scaffolding that ensures our data gets to exactly the right place, literally at the speed of light. Well, today's the day we demystify all that magic.
We structured this explainer as a tactical mission briefing. We'll be looking at the Digital Postal Service, decoding IPv4 anatomy, public versus private networks, subnetting and classes, the journey of data packets, and finally, the IPv6 future.
All right, let's jump straight into Section 1, the Digital Postal Service.
So what exactly is an IP address? Basically, it's a unique number assigned to every single device connected to a network. It helps devices identify and communicate with each other over the internet, kind of just like how a physical home address helps the post office deliver mail right to your front door. Without IP addresses, the whole shebang, websites, emails, online services, wouldn't work at all. It's the digital GPS coordinates for your data.
Now, let's clear up a super common point of confusion. How is an IP address actually different from a MAC address? Well, a MAC address is the permanent physical hardware fingerprint of your device. It's this 6-byte hexadecimal code assigned by the manufacturer, operating down on the data link layer. But your IP address? That operates on the network layer. It's an assigned location identifier. It can be static, meaning it never ever changes, or dynamic, meaning it changes depending on where you happen to connect. Basically, think of the MAC address as your device's social security number and the IP address as its current mailing address.
Moving on to Section 2, decoding IPv4 anatomy.
Okay, take a look at how this familiar dotted decimal format breaks down into the raw binary language that network routers actually read. As humans, we look at numbers like 172.16.254.1 because, let's face it, it's easy to read and remember. But computers? They process this as a 32-bit binary number. Each number separated by a dot is called an octet because it represents exactly 8 bits, a string of 8 ones and zeros.
And these 32 bits dictate the core characteristics of IPv4. Because each of the 4 octets is 8 bits long, the decimal value of each section can only range from 0 up to 255. When you do the math on a 32-bit system, you get a theoretical maximum of just over 4.29 billion unique addresses globally. Now, back when this protocol was deployed in the early 1980s, 4.3 billion seemed like an absolutely infinite amount. But, as we'll see in a bit, the world grew way faster than anyone anticipated.
Next up, Section 3, public versus private networks.
So here's how this division actually plays out in the real world. Your internet service provider assigns one single public IP address to your home or office router. This is your external-facing, globally unique identifier on the web. But inside your house, your router acts as kind of a traffic manager, assigning private IP addresses to your phone, your smart TV, your laptop. It uses something called Network Address Translation, or NAT, to act as a gateway. It translates all that private traffic from your internal devices into that one public IP whenever you request data from the open internet.
To make this entire system work globally without running out of addresses instantly, specific blocks of IP addresses were reserved strictly for private use, under a standard called RFC 1918. You've probably seen these numbers before. The 10-dot network is massive, usually used by big enterprises. And the 192.168 network? That's almost certainly what your home Wi-Fi uses. Because these are universally recognized as private and completely non-routable on the public internet, millions of homes around the world can reuse those exact same 192.168 addresses internally without ever causing a global conflict. Pretty smart, right?
All right, let's get into Section 4, subnetting and network classes.
To manage massive scale, network engineers organize IP space into distinct classes. Every address is divided into a network portion and a host portion. Say a massive corporation needs millions of devices but only one main network, they'd use a Class A space, where only the first octet identifies the network, leaving a whopping 24 bits just for hosts. On the flip side, a Class C space uses the first 3 octets for the network ID, which is perfect for having tons of small networks that only need up to 254 hosts each. Oh, and Class D? Interestingly enough, that's reserved entirely for multicast traffic, like streaming a single live video feed to thousands of users all at the same exact time.
But let's be real, a raw Class A or B network is usually way too big and chaotic to manage, and that is exactly where subnetting comes in.
Subnetting is literally the ultimate efficiency tool for network admins. By mathematically borrowing bits from the host portion of the address, they can carve up a massive, unwieldy block of IPs into precise, logical subnetworks. This means they can create isolated, secure segments, like putting all the office printers on one subnet, the secure internal servers on another, and the guest Wi-Fi on a completely separate one. It's like building perfectly organized rooms inside a giant warehouse.
This brings us to Section 5, the journey of data packets.
Think about it. When you request a web page, the data doesn't just travel to you as one giant, heavy file. That would clog the network instantly. Instead, it gets broken down into tiny little digital couriers called packets. Each packet carries a chunk of the actual data, the payload, but it also carries some absolutely crucial metadata. It packs both the source and destination IP addresses, again, those GPS coordinates. It also carries sequence information so it can be put back together, and a hop count or time to live. That last one is super important because it ensures that if a packet gets lost in the network, it eventually just expires instead of wandering the internet eternally like a digital ghost.
Let's actually follow the waypoint map a packet takes. First, it bounces from your device straight to your local Wi-Fi router. The router pushes it out to your internet service provider. From there, the domain name system, or DNS, kicks in and translates the website name you typed into its actual destination IP address. Then, boom, the packet is fired at literal light speed across the high-capacity fiber optic internet backbone. Sometimes these packets are traveling under the ocean, just zooming along until they reach the precise remote data center server they were looking for. Now, once millions of those packets finally arrive at the destination server, they might be entirely out of order, depending on the different routes they took to get there. This is where the TCP/IP suite works its magic. The Internet Protocol, IP, handled the addressing and routing to get them there. But the Transmission Control Protocol, TCP, well, it acts as the manager. It checks for errors, requests missing packets to be resent, and perfectly reassembles the payload into the correct sequence, making sure your data has flawless integrity.
And finally, Section 6, the IPv6 future. Remember when I said we'd eventually run out of those 4.3 billion IPv4 addresses? Well, to fix that exhaustion, the Internet is currently undergoing this massive, ongoing migration to IPv6. We're actively replacing the old 32-bit dotted decimal system with a massive 128-bit hexadecimal format. So instead of 4 blocks of numbers, IPv6 uses 8 groups of 4 hexadecimal digits. That's using numbers 0 through 9 and letters A through F. This isn't just a minor software upgrade, folks. It's a total architectural revolution that shifts us from a heavily limited address space to one that is practically infinite. Just how unlimited are we talking? Look at this number, 340 undecillion. That's a 340 followed by 36 zeros. To put that massive scale into perspective for you, IPv6 gives us enough unique addresses to assign a dedicated public IP address to every single atom on the surface of the Earth, and we'd still have plenty left over. Seriously, we are never ever going to run out of these.
And because this address space is so unfathomably vast, the underlying architecture gets to change too. IPv6 builds subnetting right into the address structure itself. It reserves a whopping 64 bits just for the interface ID, the host, and uses a global routing prefix along with a dedicated subnet ID. Ultimately, this eliminates the need for those complex network address translation hacks we talked about earlier. In an IPv6 world, every single device can have its own direct, secure, globally unique IP address without needing to hide behind a router.
So, we've mapped the incredible journey of the IP address, from its micro-level binary code all the way to the macro-level global network, and even peered into the dawn of the IPv6 era. But honestly, this evolution leaves us with a pretty critical, provocative question. When every grain of sand, every smart toaster, factory sensor, and autonomous car has its own globally unique direct IP address, are we truly ready to manage and secure an infinitely connected world? It is going to be a fascinating challenge for the next generation of network engineering. Thanks so much for watching this explainer, and we will catch you in the next one.